Welcome back to the lecture.
So the question is maximum likelihood estimation for ML estimation for latent variable models. For a latent variable model, both the model parameters and the density over Z needs to be estimated. Over the latent variable needs to be estimated. Why? Because of the very fact that this Z is unknown, unobserved. So we do not know what this is. So we not only estimate the parameters of the model, we also estimate the density over Z. So we do it jointly when we do a maximum likelihood estimation for the latent variable models. So let us look at how this turns out mathematically. So we have the likelihood function So I will call that as L theta, okay, for the notation sake. So L theta, L of theta is log p theta of x. This is the definition of it. And by the way, the math from now on, I will assume that we only have one data point in our data set. I will do all the analysis by assuming that we only have one data point because of ease of algebra. I mean everything that we do can be extended to n data points just by putting a summation outside which runs from 1 to n, okay. But to simplify the algebra, I will assume that we only have one data point, okay. So log of p theta x is the likelihood of x is the data point that we have, and log p theta x is the likelihood of that particular data point, okay. Now for the latent variable model, this is equal to log of, I will assume that the latent variable is discrete for now, this is p theta of x and z. Please note that in a latent variable model framework, for every data point xi you have one realization of the random variable z as well, get it. So for every image you have the, for if you take the example of that handwritten digit that I just cited, now for every image you have the thickness of the digit and all that, right. So for every xi there is a corresponding zi, but now since we are looking at only one x that we only have one z, okay, that is the way to look at it. So now this is what the likelihood is, p theta is now marginal over these two. So remember that now our goal is not only to estimate theta, which are the parameters, but also to estimate a density over z, because we do not know what z is. So suppose qz is some density over z. Let qz represent some density over z, okay. Now what happens, L theta, this is the function that we want to maximize, I will write that as p theta x and z I will just multiply and divide this qz to this particular thing. I am simply introducing this density that I want to estimate into the modeling choice, and because the density function is non-negative I can do this and nothing changes, right. Now this is equal to log times p theta x and z divided by qz. Alright, this is okay. Now what is this equal to? See, this entire thing inside the parenthesis is some function of z, correct? You can look into that as a function of z, and there is a function of z and you have a density over z, and there is a summation over the random variable z. So what is this entire thing now? That is the expectation, right? So this is the expectation of this is with respect to qz. So remember that our problem was that we had log of sum. Going back to the mixture density model, right? So we had a log of expectation has a sum. So we have this log of sum here. We don't know how to deal with log of sum. We know how to deal with sum of logs. Now you have log of expectation. We want expectations of log. Can we do something about it? Turns out we can, not exactly but approximately, okay, using something called Jensen's inequality. So if we have a concave function, then we know that expectation of a function is bounded by the function of expectation, that is Jensen's inequality, right. So let us invoke that right now here. So we have just a second. Logarithm is a concave function, right. This we have expectation of log of p theta now which one is greater? This is that, this is correct. So this was the likelihood, okay, and let us call this as some f theta of q. So I made it a function of q because depending upon the choice of q that we make, this will take a different value, correct. So I wrote that as a function of q, and this is the L theta that we wanted to maximize. So far so good, this is all algebra. Any questions on this?
The density of Z, why does it not depend on theta?
Come again?
The density of Z, it does not Q does not depend on theta. Why exactly?
We have chosen it that way. See, when I say theta, theta are the parameters of this. I mean, technically I can make it a function of theta as well, but I have chosen it to be a function of z, that is it. So when we take an example, you will see. So it is just notational convenience, that is it, okay.
Is QZ a probability mass function on Z?
Depends on the choice of z, no. If you make your z to be a continuous random variable, then it is a density function. If you make it a discrete random variable, it is a mass function.
In this case, it's a mass function.
I have made it, yeah, have I taken, yeah, in this case it is a mass function. In this case it is a mass function, yeah. All algebra will go through even if you replace this with an integral. Okay, same thing, but yeah. So see, I deliberately took it as a mass function because in our case of a mixture density, it is discrete. The latent variable is discrete.
And so being very precise, we should write expectation with respect to Z and not Q of Z, because Q of Z is a probability.
See, again notational convenience, I am used to writing expectation with respect to densities, right. But yeah, so some people write it, I write it with respect to densities because if you write it with respect to random variable, you do not know what the underlying density is, no. So I choose to write it with respect to densities, that is it, that is a notational convenience. Is this okay? So what did we just do is that, so this f theta of q, see we did two things, okay. This f theta of q is now computable since we have log of sum, right, so, no, sum of log, it has sum of log. Type terms. The other interesting thing is, so f theta of q is a lower bound on L theta. L theta, what is L theta? L theta is the log likelihood, correct? Like completely blank. Likelihood, okay. Mind is mostly an autoregressive model, you see. Conditioned on the previous tokens, it will generate the next token. So if there is an error in the previous token, it will not generate the next token. That was a joke. This is log, like L theta is log likelihood. It is also called evidence. Log likelihood is also called evidence in literature. So f theta of q is a lower bound on evidence. Therefore, its evidence lower bound. Abbreviated as ELBo. Might have heard ELBo optimization, right. So basically it is constructing a lower bound on the log likelihood and optimizing it, that is it. And this lower bound comes through the Jensen's inequality. Okay. Now the new optimization problem that we have is, we have theta star, which is the optimal parameters. So originally we had to find theta that would maximize the likelihood, okay. This was the original problem. Now instead of this, now we will find our theta stars that would maximize not the likelihood function but a lower bound on it, modified new optimization problem. Now the question is, while we want to, okay, let me call that theta star cap, while our objective is to maximize the likelihood, why are we maximizing the lower bound instead, right? Come again? Not necessarily. See, we are constructing a lower bound, not a higher upper bound. So when you maximize the lower bound, there is no guarantee about the original function. So what we are optimizing is the lower bound on the function, right? Now why are we doing it is because in the cases of latent variable models, this is the best that we can do, because the actual likelihood function is intractable, as we saw, we cannot optimize that at all. So what we do is we construct a lower bound instead by introducing another variable onto the system and we optimize the lower bound on it. Okay, this is called ELBo optimization, okay, where instead of optimizing the likelihood function, we are optimizing a lower bound on it. Now the question is, can we come up with an algorithm that would guarantee something, okay, about optimizing the original function? So EM algorithm is one such algorithm that guarantees such an optimization procedure, as we will see now. But remember that instead of solving the original optimization problem, which is finding the parameters by through maximizing the likelihood function, now we are finding the parameters by maximizing a lower bound on the likelihood function. Okay, this f theta q is the evidence lower bound that we would optimize. And please note that this f theta q is a function of q, which is the choice of the density function that we choose on the hidden variable z. Now as you can see, okay, let me just do the math and then tell you. Okay, this is what I wanted to say. We will stop here and continue in the next lecture.